We're going to look at two properties, momentum and inertia, and how these are related to each other. Let's start by defining momentum. Now, momentum is a word that we hear fairly often in our everyday language, and its everyday definition is pretty similar to its physics definition. Momentum is related to inertia, or Newton's first law, which says that an object in motion tends to stay in motion, and an object at rest tends to stay at rest. Well, momentum is tied to the motion part of inertia. Momentum can be defined as how hard it is to stop a moving object. An object that is bigger or has more mass, or that is moving faster or more velocity, is harder to stop than an object that has less mass or is moving slower. This is tied to momentum. Momentum is a vector quantity like displacement, velocity, or acceleration, so it always has a direction. Momentum is equal to the mass times the velocity of an object. When we represent this as variables, it's P equals mv, or mass times velocity. Momentum does not get its own units like Newton's applied to force. Momentum just uses the units of its components. It's the mass times the velocity, so it's the kilograms times the meters per second, or kilograms meters per second. Let's quickly look at some ways that we can change the momentum of an object. If we increase its mass, we increase its momentum. Also, if we increase its velocity, we increase its momentum. And the opposite is true for both mass and velocity. Let's calculate momentum in one example. Let's say we have a bowling ball that's rolling at 3 meters per second down the lane, and that bowling ball has a mass of 6 kilograms. Let's start by listing the things that we know. We know that the mass of the bowling ball is 6 kilograms, and we know that the velocity of it is 3 meters per second. We also know that the equation we're going to use for momentum is P equals m times v. All we have to do is to substitute in the mass and the velocity. So we will be looking at 6 kilograms times 3.0 meters per second. This gives us a momentum of 18 kilogram meters per second. Let's now look at another quantity that's related to momentum. This is impulse. Let's say, for example, that we wanted to change the momentum of an object. Let's say we have a car that's rolling down the road and we want to stop it. We know that we're going to have to apply some force to make that car slow down. But what's also important is how long we apply that force. If we only apply that force for a small moment, we're not going to change the momentum of that object very much. This leads us to the definition of impulse. Impulse causes a change in momentum. An impulse is represented by the variable I, and we calculate it by multiplying the amount of force times how long that force is applied, or I equals F times T. Again, impulse does not have its own units, but it is a combination of newtons times seconds, or Newton seconds. Now, as we said, impulse is a change in momentum. So we can actually combine the equation for momentum with the equation for impulse. This gives us what's called the Impulse Momentum Theorem. This is stated in variable form as F times T, or impulse, is equal to the change in the momentum, or delta m times v. So the more impulse we have, the greater the change in the momentum we'll have on that object. Let's take a look at a situation where we can see the value of the Impulse Momentum Theorem and how it can help to explain a lot of experiences we have in everyday life. Let's say, for example, I had to jump from a height, say a second-story window, and I got to choose what I landed on. Would I choose to land on concrete or in a pile of snow? Obviously, I would pick the snow, but we can look at the Impulse Momentum Theorem to see why it's a better choice to land in the snow. Let's start by looking at the side of the equation that deals with the change in momentum. We're going to see that regardless of the situation, whether I'm landing on the concrete or in the snow, the change in momentum is the same. In both situations, the mass remains the same and the velocity is the same, or the change in the velocity from the time I jump off the window to the time I come to rest. So in both situations, the change in momentum is the same. What's interesting is when we look at the left side, or the impulse side of the equation, the force times the time. Let's compare the impulse for when I land on concrete to when I land in snow. In both situations, we're going to look at the impulse, or the force times the time. In the case of the snow, the time is going to be much longer, I'm going to gradually slow down as I hit the snow and as I move through it. This gives me a large T for the impulse on the side of the snow. In the case of the concrete, the T is much smaller. The time it takes to come to a stop is going to be much smaller with concrete than it is with snow. Now, since the change in momentum is the same for both situations, this brings a big difference in the amount of force that's applied when you land on snow versus when you land in concrete. Let's start again by looking at the snow. Since there's a large amount of time where the force can be applied, this requires there to be a smaller amount of force to equal the same change in momentum. But when I'm landing on concrete, the time is so much smaller that this requires there to be a much greater force to get the same amount of momentum change. This highlights that the amount of force experienced when landing on concrete is much greater than when we land on something like snow. Obviously, the much greater force from landing on concrete would do much more damage than the smaller amount of force from landing in the snow. This gives us some ideas of how impulse and momentum apply to a lot of everyday situations. And it gives us some insight into how safety equipment is designed, especially things like airbags, helmets, or even padding. Each of these things tries to increase the amount of time that the force is applied, and thereby reducing the amount of force we must experience. All of these things relate to and are applications of the impulse momentum theorem.